All right, let's navigate to our IDE. So you can use Thony or whatever your preferred IDE is. Once you're in Thony, we want to be able to open up our folder. So I'm in Desktop, My Projects, and then we're working in Lab 5. Just as a double check, let's go ahead and open up our command prompt and our terminal. And inside the terminal, we are going to navigate to our folder and do a git pull. The git pull will give us the most updated files. And so I'm just navigating into my project. And then I will execute a git pull. And you can see my specific copy of the repository is a little out of date, and so it's been updated. All right, so now that I have an updated copy, I want to go back to Thony. It should do an automatic refresh, but it's possible that it doesn't. If it doesn't look like you have the right refresh, you can navigate out of there and then go back into Lab 5. But as long as you have Lab 5.0.2, that means you'll have the latest copy. So close the terminal and let's take a look at the code. The items at the top should seem fairly familiar. We're importing the library that contains the GPIO information. And then I have two variables that I'm setting. The variable that will be associated with physical pin number 11 is known as the pull-up resistor pin, and pin 13 is the pull-down resistor pin. In the setup section of the code, we should see that we are setting the GPIO pin mode, or set mode, into the board, so physical location. And then the next line of code, GPIO.setup, we're using the pull-up resistor pin variable, so that would be the same as putting an 11 in here. Then we are indicating that this will be an input pin rather than an output pin. And then finally, we're saying that we want to use a pull up or down resistor. So the pull up down value, in this case, we're going to set this to be a pull up resistor. So pull up down equals GPIO.PUD_UP makes this a pull up resistor. The second line, or the next line after that, is very similar, except we're using the pull down resistor pin variable, which would be a 13 in this case. We're saying that this is also an input, and we're indicating that we want this to be a pull down resistor. Notice that the value pull up down is the same on both lines. However, what we're setting the value to, one of them we're setting to be a pull up resistor, and the other we're setting to be a pull down resistor. Next, we want to add a function of the GPIO that's known as an event detection. So we do GPIO.addEventDetect, and we're saying that we want to determine when something happens to this specific pin. So the first one that we're addressing is the pull-up resistor pin, which is physical pin number 11. And we're saying that we're looking for any type of feedback that we receive on this pull-up resistor pin. The callback is simply a way for us to be able to identify a function that will be executed when there is an event detected on this pin. Bounce time is simply just a way to be able to delay a little bit the information that's received, so that if you touch it, the pin to ground, and then let off just barely and touch it again, that it doesn't just keep spinning up that function and calling that function. So it gives a little bit of delay time. The next line is exactly the same, except now we are using the pull down resistor pin, so pin 13, and now it has its own function called pull down sense. Below the setup, we'll find both functions, pull up sense function and pull down sense function. Remember, these functions are called when there is an event detected on that particular pin. So when pin 11 has an event detection, it calls pull up sense. When pin 13 has an event detection, it calls pull down sense. We'll now see the code functioning when we connect up our breadboard. So here I have our breadboard, and we are connecting to pin number 11. Remember, pin number 11 is labeled as GPIO 17, so it's physical pin number 11. And the other pin that we'll be working with is GPIO 27, which is physical pin 13. We'll be using a jumper wire coming from physical pin number 11 just for ease of testing. So we're going to put the jumper wire on pin 11. So this is on the grid A6 in my example. And then the other end of the jumper wire, I'm just going to move to the bottom below the cobbler into location A26. You could put these jumper wires anywhere on your board. I've just been calling them out specifically because we're going to have several jumper wires on here, and I want to make sure that you have the same value as I do. We'll next create a test point for our pin 13. So I'm connecting GPIO 27, which is physical pin 13, at B7 down to the test point at coordinates B27. We'll need to access both the power and ground coming out of the Pi. So in this case, we're going to be using the 3.3 volts. So here I'm running a jumper wire at pin number 1 in location B1 and just jumping it across the board to the positive rail. So remember, that positive rail, it goes all the way down to the bottom where it's indicated also positive. So that's a connection all the way to the bottom. The next thing we need is a ground. This will make it a little bit easier for testing, similar to the positive. So I'm going to get the ground that is in position pin 6, which is J3 coordinate, and I'm going to connect that to the negative rail. Once again, this matches the positive rail in that it goes from the very top to the bottom of the board. This is simply just for convenience. You could connect to any ground on the Raspberry Pi. They all share the same. I just grabbed this one because it was the most convenient. Now I need a jumper. This is just simply for testing. I'm going to stick it in the positive rail, doesn't really matter where. And the other end, I have it here in F26, but we'll be moving it. So just to hold it in place, stick it in one of the pins on the lower end. The final test pin that we will need is a ground, so connect to the negative rail, and then the other end, I have mine connected at F28. As long as you don't put it on the same row as the positive, it doesn't really matter what the other side is connected to. We'll be moving this as we do our tests. Now that our board is set up for testing, we want to run the program associated with this lab. Go ahead and open up your terminal, and we want to get into our folder. And then let's do a git pull to ensure that we have, one more. Now we do our git pull. Now we have make sure we have the most updated copy of the code. And we will be executing lab 5. So here we have our different labs. We're going to do a cd lab 5. And then inside of lab 5, we will be running lab 5.0.2. So Python lab, remember you can push your tab key. And then if you push 2 and then tab again, it auto fills that in. And then enter to execute the code. We're now ready to make some measurements, so we'll need a multimeter in order to do this. The multimeter leads that I'm using are slightly modified just to make it easier to be able to capture the measurements that I'm making. Yours may not seem as clean as this picture, but as long as you're measuring in the correct location, it should work for you. Hopefully you recall that a breadboard is used in order to do some experimentations on electrical components. The way that a breadboard works is the rows, which are identified by the numbers that are on the left or right of the row, are all connected together. So every point along pin number 26 or row number 26 is electrically connected. So now that I have my red meter lead here on row 26 and my white jumper wire on row 26, those are essentially touching each other. And so we simply just moved down the jumper wire just to make it a little easier for measuring. But you can see that that is essentially what I'm doing here is I'm measuring the voltage of pin 11 GPIO 17. We also need to connect the black meter lead to the ground bar. So mine's tucked away down here, but you can see it pointed to by this black arrow. So we have our black meter lead on ground, and our red meter lead is reading the voltage at pin number 11. I pulled up the setup portion of our code to help remind us of what is happening here. So your code should be executing right now, and you should be getting a value of 3.3 volts. If you're not, you need to check whether or not your code is running and that you have the meter leads and jumper wires in the correct position. So here we see on the second line is the code that we're concerned about. We set pin number 11, so pull-up resistor pin variable is pin number 11, to be a pull-up resistor. A pull-up resistor will have 3.3 volts until a switch is closed and it is grounded, and then it will have 0 volts. So a pull-up resistor, without doing anything to it, should be 3.3 volts in our case. Alright, here we have a pull-up resistor example to try to make sure that we're clear on what's happening here. So the dash box indicates that this is the inside of the Raspberry Pi. So on a vehicle you would see something very similar that would show like the body control module, and it would have a dashed line that indicated that this is inside of the module. So this is inside of the Raspberry Pi. At the very top I have a plus V that indicates that this is a pull-up resistor. The plus V could be 3.3 volts, 5 volts. If it was on a different system, it could be even higher. So in our case, we're running 3.3 volts. The below that is a fixed resistor. That fixed resistor is used to drop the voltage when the connection is made to ground. I have placed inside here that there's not a little multimeter inside of the module, but I've placed one here just so that you can help to understand, so that it will help you understand what's occurring inside here. So the red line is the voltage sense. This is how the computer identifies what the voltage is on that particular pin. In our case, we're looking at pin number 11. So in this case, if we were to read the voltage at pin number 11 after the resistor, we would get a value of 3.3 volts. The reason we get 3.3 volts is the circuit is not complete. I have an open in the circuit because of the switch, so current is not flowing through the circuit. When current is not flowing through the circuit, a voltage drop does not occur at the resistor, so we remain with a voltage value of 3.3 volts. So in order to ensure that you correctly understand what we're measuring here, that internal voltage sense, that's not the representation of the meter reading that we're currently getting, or the meter and its position in the circuit. So here I have drawn our meter. This is the meter as represented by the one that we see in the image. Where we're checking for voltage is on the exterior of the Raspberry Pi. So that black wire that's coming out of the dashed wire is physical pin number 11. So when we're making this measurement, we're actually making it external. It just happens to match the internal voltage sense measurement. Alright, now let's demonstrate what happens when we close the switch, or when we ground the pull-up resistor. So take that ground jumper wire and we're going to bring it over so that we ground the row number 26. So now our row is grounded and we should see a voltage value of 0. You should also see on your terminal an indication that the pull-up resistor has been triggered. Now I have the schematic with the pull-up resistor and the switches in the closed position. We just simulated this with the jumper wire, so we have grounded the circuit. Now what should occur is current will be flowing through the circuit from the positive V or VCC through the resistor. At the resistor, the voltage will drop. It should drop all of the voltage at the resistor. The remaining voltage after the resistor should be very close to 0, so our value would be 0 volts. This is how the computer identifies that the switch is in the closed position. Using a pull-up resistor, it knows that at a value of 3.3 volts or a little less than that, that is in the off position. Any voltage that is low, like a 0 volts or a little bit more than 0 volts, that would indicate that the switch is in the on position, thereby verifying and understanding what the condition of the switch is so that it can determine what action to perform next. You should now have the information that you need in order to test the pull-down resistor. The pull-down resistor, make the same measurements that you made with the pull-up resistor, and then you'll notice that you utilize the jumper wire that is connected to positive in order to trigger that switch to the on position. So go ahead and set up your meter and trigger the pull-down resistor. Hopefully you took the opportunity to figure this out on your own. What you should have seen with the switch in the on position or the positive jumper wire connected to pin 13 is that the voltage went to a 3.3 volts. The opposite happens when the switch is in the off position, so without any positive connected to it, you should have seen that you had a value of 0 volts. If you did not receive these values, talk to your instructor and see what went wrong. Now that we have a clear understanding, hopefully, of pull-up and pull-down resistors, we'll now be utilizing them in a project.